Okay, let's start. Today we are going to talk about the k-means clustering, mixture of Gaussian, and expectation and maximization. From the last week, we've talked about the k-means clustering and mixture of Gaussian model, and today we will provide the expectation and maximization method that that solve the mixture of Gaussian problem. Okay, before starting, let's recap the k-means clustering and Gaussian mixture model. K-means clustering was the unsupervised learning. So there are so many applications of unsupervised learning, right? So comparing to the unsupervised learning do not need the class label in the training data set, right? So so what is the clustering? So clustering is to find the prototypical point. So u1, u2, mu1, mu2 through the mu k when k is the number of the cluster, and cluster assignment or the cluster membership Zn for all n is equal to 1 through the n when n is large, n is the number of samples, right? Input vector xn in the RD space, right? So when you think of the clustering problem in the 2D space, this green dot is the input vector, right? Or input sample, right? Then we want to separate those input samples in terms of their similarity, right? So let's say there is a two cluster, that the one cluster was here and second cluster is here, right? Then what we want to do is to find out the cluster center or tropotype point here, right? That represent each cluster. Then we want to find the cluster assignment for each sample that measured. This sample is assigned to the cluster 1 or cluster 2. Okay, so this is what we want to do. So the loss function for the k-means clustering is as follow. We want to find the z and mu, right? So z is define something like that. When we define the input x as a RD space, then the size of the large X or the data matrix is something like n by let's say k by d, right? So k is the what is that? Yeah, k is the sorry about that. So yeah, x is the okay, so one x vector in the RT space, right? So d-dimensional feature, and we have the n sample, then we can represent the size of the x as a d by n. Okay, so this is the input vector, and what we want to do is to find the two matrix. The first matrix is Z here, right? So Z is the cluster membership. So the size of the Z is the n by what? N by k. Okay, so number of the cluster. So for each sample, we have to find the cluster membership, right? Then the matrix mu is the mu have the k columns with the d-dimensional mu k, right? So the size of the mu is the k by d. Okay, so this is the goal of the k-means clustering. So by minimizing this loss function, we can find out the mu and z, right? So this is the k-means clustering algorithm. So k-means clustering algorithm is to there are consisting of the two sub optimization. The first optimization, we find out the Zn given mu, right? And in the second optimization, we find out the mu k given Z. Okay, so this is the alternative minimization technique, right? So this is the first step, right? So from from the two cluster centroid, we compute the cluster membership Zn, right? From this from this rule, right? Then given Zn or given the cluster membership, we update the cluster centroid mu1 and mu2, something like that, right? So this is a k-means clustering algorithm. Actually, k-means clustering algorithm is really simple, so and really intuitive, right? So there are two sub problem that can be solved by iterative update rule, right? So this is very intuitive, but this simple algorithm is related to the expectation and maximization algorithm that we will see today, right? So we will see what is the difference between the k-means clustering algorithm and EM expectation and maximization algorithm. Okay. Okay, so this is the overall procedure of the k-means clustering, right? So yeah, so this is the examples, right? And we also talked about the probabilistic interpretation of the our model or our classifier, right? So we already know the what the Gaussian random variable or the Gaussian random vector is, right? So the Gaussian random variable is defined by mu and sigma, right? The shape of the Gaussian random variable or the Gaussian random vectors, something like that, right? So the left hand side is the 1D case and the right hand side is the 2D case, right? Okay, so we have shown that the simple linear regression model can be interpreted by the log likelihood rules, right? So something like this, right? So yeah, when we maximize the log likelihood of the linear regression loss, it is the it is the almost similar to the MSE loss that is the popularly used in the linear regression problem, right? So yeah, here equivalent equivalent at the equality, right? So similarly, we can define our k-means clustering loss in terms of the probabilistic model, right? So something like that. So we derive our k-means clustering loss function here, right? Okay, so this is the probabilistic model for the k-means clustering, right? And what was the limitations of the k-means clustering? The first one is the clusters are first to be the spherical, right? Like our here, like a black circle, right? Then in some case we need a elliptical shape of the cluster, something like this, right? This and this, or this, like that. So, and another limitation is that each samples can belong to the only one cluster, So this is called the hard cluster assignment. So to elaborate these two kinds of limitation, we introduced the Gaussian mixture model, right? So there are two motivation, elliptical cluster and the hard assignment. So the first limitation can be solved by introducing the full covariance matrix mu sigma k instead of the isotropic covariance, right? So here, and the second, the limitation is overcome by the by introducing the Zn, which is the random variable that follows the multinomial distribution, right? So that's why the Gaussian mixture model is called the soft clustering method. So yeah, so from this definition, we introduce the loss function for the Gaussian mixture model here, right? So we introduced the latent unobserved variance Zn, right? So our goal is to find this theta that consisting of the mu 1 through the mu k and sigma 1 through the sigma k, and the pi is the probability of the each cluster. Okay, so what are we going to do? So first of all, by marginalizing Zn, we can reformulate this probability in terms of the Xn, right? So finally, we derive the probability of the Xn given theta here, something like that. Okay? So, so our goal is to get the maximum likelihood estimate of the theta here. Okay, so okay, this is our final goal. Okay, so this is our final loss. Okay, let's see the maximization today. Okay, let's go back to today's lecture. Okay, so the goal of the expectation and maximization, or called the EM algorithm, is to compute the maximum likelihood for the Gaussian mixture model, right? For example, when define, where's that? Yeah, here. So when we define the theta as the pi k, mu k, and sigma k, right? Then loss function for this theta is something like that. So we want to minimize this loss function in terms of the theta here, right? When the theta is here, right? But as you can see here, minimizing this loss function is difficult due to the log outside the term, outside the summation here, right? So it is hard to decompose this loss function in terms of each component, or the each cluster terms, right? So we need another technique to minimize this loss function. So that's why we introduced the EM algorithm today. So EM algorithm provides an elegant and general method to optimize such optimization. It used the iterative two-step procedure, where individual steps usually involve the problem that are easier to solve. So when you remember the k-means clustering algorithm, the k-means clustering algorithm is also consisting of the two steps, right? So similar to the k-means clustering algorithm, EM algorithm also consists of the two steps. Okay, let's see what it is. Okay, here is the algorithm. So first of all, we have to initialize the theta as a theta 1, and we will iterate the two steps. The first step is called the expectation step, and second step is called the maximization step. Okay. In first of all, in expectation step, we compute the lower bound to the cost cost L of theta, such that it is the tight at the previous theta t. What does it mean? Okay, let's see the loss feature here. Okay, let's say x-axis means the theta that we want to solve, right? And y-axis means the loss in terms of the theta, right? Let's say our loss function, shape of our loss function, it looks like that, right? And as we discussed the previous slide, it is really hard to optimize this L of theta directly. So what we want to do, we want to introduce the new loss function that is easier to solve. So let's say there is the quadratic loss function, something like that. It's much easier to solve, right? So, okay, let's say this is the initial theta here. Then instead of the solving this loss function, we can solve this sub-optimization problem here. So this is the new new theta, right? So from something, let's say this is a theta 2, right? So from this theta 2, we can make a new another sub problem, something like that, and then we can solve the this quadratic optimization here. This is a new theta 3, new theta, or the theta 3. Then we can find the new theta value, right? So rather than solving this original loss function, we just optimize from initial theta 1 through the theta 2 and theta 3, something like that. And this is a much easier strategy than optimizing the L theta. Okay, so in here we call this is the L of theta and theta t. So here the theta t means the previous theta, and this term is defined given previous theta t. Okay, so today we will see what is the L of the theta and theta t, and how can you optimize this one. Okay, and fortunately here L of the theta t is equal to sub loss function L theta t comma theta t. Okay, so this is the equality property. So as you can see here, the L theta is larger than or equal to the L theta given theta t. Okay, and L theta t is equal to the L theta t comma L theta t here, right? So if we define this L sub loss function L theta comma theta t, we can solve the L theta comma theta t in the expectation step. Okay. Then in the maximization step, we update the theta, something like this. Find the argmax in terms of the theta by maximizing this sub loss function here. So this will be the new theta. Okay, here, right? Here. So So this is the expectation step, right? So by iteratively solve this expectation step and maximize step, we will find the converged values in terms of theta. Okay, so this is the summary of the EM algorithm. So people derive this L of the theta comma theta t. We need some mathematical technique. So just call the convexity of the negative log, or the concavity of the log. Okay, let's see what it is. Okay, first of all, what is the shape of the log? What is the shape of log function? Something like this, right? When we say this is a log R, right? So, and x-axis means the log just R, and y-axis means the log R right here, like this, right? So let's say there is the R1, R2 through the RK here. Okay, so first of all, given non-negative weight Q such that the summation of the PQ QK is the okay, where is that? Yeah, here. So it should be 1. So when summation of the QK is 1, then okay, so then the sigma K QK RK here, right? So because this is the linear summation of the R1 through the RK, right? Then the log K QK here, right? Right? And what is the just log R1 here, right? And log R2 is here, right? Then what is the linear summation of the log R1 through the log RK? Where is that? It may be here, right? So as you can see here, this blue line is always the larger than this black line, right? So from here we can define the very interesting inequality. So let's say look summation of the QK RK, right? So this log summation of the QK RK is larger than summation of the QK log RK. So like this from this relationship. So it means that we can derive this one from the property of the log function. Okay, actually this one is called the Jansen's inequality, which is very popular in the machine learning field. So if you are interested in, so please find out what it is. But today we will just skip of the proof of this inequality. But this is just the Jansen's inequality of the log function. Okay, so we will use this property. Okay, So in the expectations tab, we will find the lower bound of this term here. If you remember the previous slide, it is the difficult because of the log outside the summation, right? Then we want to introduce the new term, new summation term, like Q1 KQN, right? QKN pi K F X M given mu K and sigma K. Okay, we just introduced this term, right? And then this QKN is here, right? And this term will be the RK here, right? Right. Then from this inequality, we will find the new term, something like the summation QKN log RK. Okay, let's say this is RK, right? Right? With the lower bound, right? Right. So this is some property of the log function, right? So this is called the new loss function for the RK in a given R theta t, and it was the original loss function. Okay, now we have the new loss function for the theta, right? Then by introducing the QKM, what is the QKM? We can define the QKM something like this, right? So with the pi k, mu k, sigma k here, right? So when you here, so finally, so set loss of the theta and given theta t, we have the new term, something like that. And when we put this QKN here, this term is the equation consists of the pi k, mu k, and sigma k, right? So from this new loss function, we will solve the pi k, mu k, sigma k much easier than the previous original L of the theta. Okay, now we have the new loss function. Then let's find out how can we solve this loss function. Okay, so first of all, this term can be decomposed from now on, right? So summation are here, right? So QKN here, and previous term can be decomposed as the three kinds of term, right? This term is only related to the pi k, sigma k, mu k, pi, sigma k, and pi k, right? Then we will find this variable, right? So before that, what is the t? This is the iteration index. T means the tth iteration, because this EM algorithm is the iterative optimization, right? Then how can we minimize this term? How can we minimize? We will just differentiate this loss function in terms of mu k and inverse sigma k. By the way, why we need the inverse sigma k? Because there is the Gaussian term here, Gaussian random variable here. So the Gaussian random variable looks like this. Right? So from here, by just minimizing the inverse of sigma k, we will easily solve the we will easily differentiate this loss function, right? So anyway, by minimizing the loss function, okay, let's say differentiate in terms of mu k of the L theta given theta t here with the equality with the 0 here. We will find the new mu k here, and by finding out the difference t, we find out this one. Okay, so from here mu k of the next iteration is something like that, and sigma k for the t plus 1 iteration is something like that. Okay. Interestingly, here, actually this term is the RT vector, right? So this term is the T by T matrix, right? So this is also T by the matrix, T by the matrix term. Okay. Okay, so now we have the two term mu k t plus 1 and sigma k t plus 1 given mu k t and sigma k t and pi k t. Okay, so and we also need to estimate the pi k, right? But compared to the mu k sigma k, there is the one constraint for the sigma k, pi k, of the fact that they sum to 1, right? From here, right? So this is the our previous lecture, right? Okay, so therefore we need to introduce the Lagrange term. Maybe you are not familiar with the Lagrange term, but this is just a simple. Okay, let's say we have the original loss function here, and by using some constant lambda, we just add this term to the original loss function here, something like that, right? Because this constraint was the something like that, and here. So and then this loss function is called the modified unconstrained objective. So by solving this loss function, rather than just solve this one like this, then we can derive the new pi k t plus 1 here, right? So by differentiating this loss term with respect to the pi k and set to 1, set to 0, so we will get the following, the update here. Okay, so this is the maximization step, right? So okay, it was the pi k, and here, right? Right, like that. Then, okay, this is a maximization step. And okay, let's summarize the expectation maximization algorithm for GMM model. Okay, first of all, let's initialize the mu1, sigma 1, and pi k, and then iterate between the expectation and maximization step until the L of the theta stabilized. Okay, so first of all, in the expectation step, compute the assignment q, k, and t. Okay, so q, k, and t was defined something like this, right? Here, right? And then we can compute the loss function theta t by using this one, right? What's that? This is the marginal likelihood, or just cost, right? Then in the expectation step, in the maximization step, we can update mu k, sigma k, pi k using the new using the following equation here. So those new mu k, sigma k, pi k can be computed by previous the qk and t here, mu k t plus 1 here. Okay, so this is the maximization step. This is just the computation, right? So this is just the computation of the mu k, sigma k, and pi k, right? So by iteratively solve this expectation step and maximization step, and by computing the cost at each iteration, we will see the stabilization of this cost function. Then when the cost is converged, we can finish this algorithm. Then we will get our mu, sigma, and pi. Okay, this is just the summarization of the expectation and maximization algorithm. Okay, so let's visualize this one. Okay, first of all, we have the samples here. And first of all, we need to initialize the this mu, sigma, and pi. Okay, let's say we have the two cluster here, this one and this one, right? First of all, what I want to do in the expectation step, we have to find the cluster membership here, QKN. So QKN means for each sample, compute the QKN for each sample n and for each cluster k, right? So when you see this one, the red dot and blue dot means this red dot contain in this red cluster, and blue dot means the blue samples contained in the blue cluster, right? So in here, in the middle point, this one is the similar probability that contains the cluster 1 and cluster 2. Okay, so this is the soft clustering, right? And in the maximization step, we will update the mu and sigma here. Mu and sigma. Okay, like that. So update the theta consisting of mu, sigma, and pi. Okay. And then in the next iteration, E step, update the QKN here, something like that, right? And maximization step here. So by evolving the iteration, derive the L is equal to 2. L means the number of iteration, and L is equal to 5, and L is equal to 20. We will find out the cluster, something like that. So comparing to the K-means clustering, this is much this is much more effective algorithm that separate even for the non-linear or non-rigid data distribution in the training data set. Okay, so this was the expectation and maximization algorithm. Interestingly, when we let the covariance be the diagonal, theta k is equal to the sigma square, then EM algorithm is same as the K-means clustering algorithm as decreasing the sigma square. So when we have the large sigma square and when we have the small sigma square, like that, by decreasing the sigma square, the shape looks like the theta function. So what does it mean? Okay, if you see this one, QKN, actually this term was the exponential term, right? With some constant, with the sigma square xm minus mu k, right? Something like that. So if we decreasing this one to 0, right? Then this term will be the 1 or 0 when cluster K otherwise 0. In this case, this QKN is equal to the ZKN in the K-means clustering algorithm, right? So in K-means clustering algorithm, so in other words, by decreasing this sigma square, then this expectation and maximization algorithm will be the K-means clustering algorithm. Okay, so this is the relationship between the K-means clustering algorithm and expectation and maximization technique. Okay, so this is the end of today's lecture. Before finishing, let's summarize what we have done from this last week to this week in Korean. 이제 저희가 저번 시간부터 봐왔던 것이 이제 Unsupervised Learning에 대해서 첫 번째로 소개를 했습니다. 그래서 이제 보면 사실 Unsupervised Learning이라는 거는 이제 트레이닝 데이터셋에 이제 슈퍼바이즈드 라벨이 없을 때 어떻게 이 데이터들을 마이닝을 해서 또는 분석을 해서 우리가 원하고자 하는 클러스터들로 잘 나눌 수가 있을까라는 문제를 푸는 건데, 이제 가장 간단하게 사실 K-means 클러스터링 알고리즘이 첫 번째 나왔었는데, 사실 이 K-means 클러스터링 알고리즘이라는 거는 사실 어떤 경험적 파인딩에 기반을 둔 기술이었습니다. 무슨 얘기냐면은 우리가 잘 정의된 로스 펑션 시작하는 것이 아니라 어떻게 하면 이 클러스터링을 잘 할 수 있을까로부터 시작을 해서 우리가 클러스터의 어떤 센트로이드를 정의하고요. 그의 멤버십을 ZN을 정의를 해서 이렇게 이터레이티브하게 설빙하면은 더 우리가 원하고자 하는 클러스터가 나올 수 있지 않을까라고 해서 K-means 클러스터링 알고리즘들이 제안이 되었고, 이제 이런 알고리즘들을 수학적으로 잘 모델링을 해서 정리를 해보니까 이러한 로스 펑션이었고, 이제 이러한 옵티마이징 방법들로 풀 수가 있었다 라는 것이었죠. 이제 이게 서머라이제이션이었는데, 근데 이제 이게 말했던 아까 다양한 한계점들이 있어서 이제 가우시안 믹스처 모델을 제안을 했고, 이제 이걸 풀기 위한 EM 알고리즘들이 제안이 됐습니다. 오늘 배웠던 방법인데, 이제 막 수학적인 것들을 따라가다 보니까 이제 이런 EM 알고리즘들도 우리가 K-means 클러스터처럼 이터레이티브하게 설빙을 할 수가 있겠다라고 정의를 내렸고, 근데 K-means 클러스터링보다 좀 더 이제 파라미터들이 많아지는 거죠. 우리가 찾아야 되는 파라미터들이 많아져서 여기도 보면은 이제 우리는 이제는 K-means 클러스터링에서는 뮤만 찾았던 것이 아니라 EM 알고리즘에서는 뮤랑 시그마랑 파이를 한 번에 찾아야 되는 거죠. 그래서 익스펙테이션 스텝에서는 기존의 로스 펑션이 아니라 오리지널 로스 펑션이 아니라 어떤 서브 옵티멀한 로스 펑션을 새롭게 제안을 하고요. 이제 그러한 서브 옵티멀을 풀었을 때 QKN을 구할 수가 있고, 이제 이러한 QKN을 가지고 맥시마이징 스텝에서는 새로운 뮤랑 시그마랑 파이를 찾습니다. 그래서 이러한 현재 이터레이션에 찾아진 뮤랑 파이랑 시그마랑 파이를 가지고 또 새로운 익스펙테이션 스텝에서 어사인먼트를 찾고 다시 한번 업데이트를 하고, 이제 이러한 방법을 이터레이티브하게 설빙을 하는데, 사실 이러한 익스펙테이션과 맥시멈 스텝이 K-means 클러스터링에서의 two alternative 스텝이랑 똑같았다는 거죠. 그러다 보니까 여기서의 시그마를 0으로 보냈을 때 사실 EM 알고리즘이랑 K-means 클러스터링이랑 똑같은 알고리즘이 됐다라고 저희가 정의를 내릴 수가 있는 겁니다. 사실 신기한 알고리즘이죠. 그래서 이제 저희가 이제 오늘 K-means 클러스터링, GMM, EM을 정리를 내리면서 이제 오늘 제가 말씀을 드리고 싶었던 것들은, 사실 이제 이런 방법들이 딥러닝 전부터 쓰였던 방법이고 실제로 딥러닝에서도 많이 쓰이긴 합니다. K-means 클러스터링이나 EM이 사실 주류 분야는 아니지만, 왜냐면 이제 딥러닝에서는 새로운 이제 언슈바이드 방법들이 나오고 있거든요. 그래서 이제 그러한 방법들은 이제 다음 저희가 후반부 강의들에서 보게 될 거지만, 실제로 이러한 것들이 이 방법, 그러니까 EM이 뭐고 K-means 클러스터링이 뭔지를 아는 것이 중요한 게 아니라, K-means 클러스터링부터 로스 펑션이 뭐고, 그 로스 펑션부터 GMM이 뭐고, GMM을 어떻게 EM으로 풀었을 때 로스 펑션들이 이 스텝들이 정의가 되고 그 스텝이 다시 K-means랑 연결되는, 그러니까 이 연결고리를 사실 저희가 이해를 하는 게 훨씬 더 중요합니다. 그러니까 이러한 방법론적인 거는 사실 저희가 위키피디아나 뭐 구글에 보면 사실 나와 있고, 이제 이러한 방법들을 외우는 건 사실 큰 의미가 없는데, 이러한 방법들이 어떻게 디라이브가 됐는지를 저희가 명확하게 이해를 하면, 뭐 저희가 이제 딥러닝을 통해서 저희가 각자의 문제들을 풀고 있을 때 이러한 방법들을 어떻게 다시 한번 정의를, 이러한 K-means나 EM의 어떤 릴레이션십처럼 우리가 원하고자 풀고자 했던 문제를 언슈어바이드로 어떻게 잘 딜라이브를 해갈 거냐, 어떻게 잘 전개를 해갈 거냐 하는 새로운 인투이션들을 얻어갈 수가 있겠죠. 그게 이제 저희가 패턴 인식 클래스를 듣는 이유이기도 합니다. 네. So this is the end of today's lecture. In the next lecture, we will introduce the principal component analysis, or called the PCA algorithm. This is the another unsupervised learning technique comparing to the K-means clustering or the EM algorithm. Okay? Thank you.